Alright, let's go ahead and evaluate this integral. We have the integral over the four-dimensional Euclidean vector space called R4. And the function we're integrating is e to the negative inner product of psi, which are spinor fields, with the second order internal part of the Dirac operator for fermion fields acting then on the spinor fields, minus the inner product of boson fields with the internal part of the Dirac operator for bosons then acting on the boson fields. So the first thing that we can do here is split this up between the fermionic and bosonic parts. So this is still over R4, and our first part is going to be the spinor part. d psi, and the second part, of course, is going to be our bosonic part. So we'll have another integral here multiplied into it. Okay, so now where do we go from here? Let's go ahead and just call this integral here, the bosonic part, I sub phi. So we'll write that out and know that this multiplies into this integral over R4 of our fermionic phase factor. Alright, so what can we do now? Well, first, let's go ahead and just solve this integral, because once we solve this integral right here, we're going to more or less know the general form that this integral here is going to take, because they're both at Gaussian integrals. But let's figure out here what this operator is for. So on the right side, we're going to draw a line. This is where we're going to be doing all of our linear algebra. So our Dirac operator for the fermionic sector can be written in terms of the transpose of a symmetric n by n matrix with some other diagonalizable matrix F here, acting then on S, where F gives us a 4 by 4 matrix, since we're over R4, of mass eigenvalues down the diagonal. So that's our matrix F. Okay, so what can we do with this information? Well, if we can write our second order Dirac operator in terms of S transpose F and S, let's go ahead and rewrite that in terms of this over here. So we still have I sub phi of the integral over R4 of e to the negative inner product of psi. Now we're going to rewrite the Dirac operator. S transpose, acting on F, acting on S, all acting then on psi. And this is, of course, integrated in respect to the spinor field psi. Okay, so that's pretty good. But what can we do now? Well, due to the nature of the inner product, this S transpose can actually be transported over to the left side of this inner product to just be a symmetric matrix S acting on psi. So I sub phi of the integral over R4 of e to the negative inner product of S acting on psi with F and S acting on psi. Okay, so now all we have to do is figure out what we're going to do for our substitution to help us solve this integral. to really exploit and show the Gaussian integral underpinning all of this here, because this here is a quadratic form. So this is of the form e to the negative x squared, and we know that a Gaussian integral ranging over the real numbers, negative infinity to infinity, of the function e to the negative x squared in respect to x is just equal to the square root of pi. So that's going to help us here. We have very nice symmetry. So let's do a substitution on that which occurs twice in our inner product, now s and phi. Let's allow s acting on phi to equal this operator x hat. This is going to be a 4 vector. Okay, so if we go ahead and do that, we need to figure out what is our differential going to be. Well, d psi is going to equal, we're going to need a scaling factor called the Jacobian, the absolute value of the Jacobian, dx hat. So what's the value of our Jacobian? Well, due to the nature of our diagonalizable matrix, the Jacobian can only possibly take one of two values, -1 or 1. But because we have an absolute value around it, the only value that could possibly be is 1. So d psi is not just almost dx, it is exactly equal to dx hat. And our bounds of integration are still going to be over R4, negative infinity to infinity. So let's go ahead and fill in this substitution. So filling in this information, we have I sub phi times the integral over the same bounds, which is R4, of the function e to the negative inner product. S times psi, we agreed, is equal to this 4 vector x hat, with this matrix F acting then on the 4 vector x hat. And our differential d psi, we agreed now, is in respect to the x hat operator, the 4 vector. Okay, so now that we have this information, what can we actually do? Well, let's go ahead and work on this inner product. Namely, let's start on the right-hand side, the F matrix multiplying into the 4 vector. So F times x hat is just F, which is our 4 by 4 matrix here. One, two, three, 4. So these are all positive, real valued eigenvalues. And this multiplies into our 4 vector here, which is just going to be x sub 1, x sub 2, x sub 3, and x sub 4. Well, this just creates another vector in R4. Let's multiply these alone right on down the line. So we have lambda sub 1 times x sub 1, lambda sub 2 times x sub 2, lambda sub 3 times x sub 3, and lambda sub 4 times x sub 4. And remember, these are all technically x hats. So let's go on with that. So what we actually have then is this inner product right here. But this is just going to equal the 4 vector x sub 1, x sub 2, x sub 3, and x sub 4, then acting in conjunction with this 4 vector here, Then we have lambda sub 4, x sub 4. And then we're going to close these brackets here to show that we're working on an inner product here. We just multiply these across and then add up the sums of the products. So this whole inner product is just going to equal, well, we're going to have lambda sub 1. The x's are now going to square. So we have x sub 1 square. And we're just going to add this up 3 more times now. Plus the 4th sector. Just like that. Now I'm just kind of running out of room here and kind of bumping into things here, but hopefully you can see what's going on here. The interesting thing here is that we have a negative sign that distributes through the inner product. So this now becomes our new integral here. We still have the integral over R4 of e to the negative. Now let's plug this in down the line. Minus dot 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 all the way up then to the 4th term here, which is lambda sub 4 x sub 4 squared. This is still in respect to x hat. So now you can see this is the Gaussian integral because we have a factor of e to the negative x squared down the line here. So let's go ahead and distribute that across individual integrals because we can then have e to the power of this, e to the power of the 2nd term, e to the power of the 3rd set of terms, e to the power of the 4th set of terms. So we really have 4 integrals right here, plus or times the additional 4 integrals from I sub 5. So let's go ahead and write these out explicitly. We're going to go up here now. We have I sub 5 times the integral over R4 of e to the negative lambda sub 1 x squared sub 1 dx sub 1 times the integral over R4 dot dot dot. Well, really this is not over R4, it's actually just going to be over, because we're going to split it up between 4 integrals from negative infinity to infinity, so that effectively combines the contributions of all R4. So these are just going to be over the real numbers. Let's go ahead and make some more room here. E to the negative lambda sub 4 x squared sub 4 dx sub 4. So here we are. Now on each one of these we're going to get a factor of the square root of pi divided by the square root of the eigenvalues that are down our diagonals. So for example, this will equal I sub phi times the square root of pi over the square root of our first eigenvalue. That's what this first integral is going to equal to. And now we do this 3 more times for the rest of the integrals. Square root of pi over the square root of lambda 2 times the square root of pi over the square root of lambda 3 times the square root of pi over the square root of lambda 4. So that's pretty interesting. This all combines into I sub phi. Multiply all of these square roots of pi in the numerator to get, well, we lose the square roots altogether. And we just end up with pi squared over the square root of the sums, or the products rather, of these eigenvalues down the diagonal of this matrix. But that's just equal to the determinant of this matrix right here. So this is I sub phi of pi squared over the square root of the determinant. of our matrix F. But due to the condition up here, the determinant of F is the same thing as the determinant of the fermionic part of the Dirac operator. So we can then just write this as I sub phi times pi squared over the square root of the determinant of that Dirac operator. Now, the same thing holds for I sub phi, but we're going to get the determinant of the bosonic part of the operator with another factor of pi squared. So multiplying this in here, we have pi to the 4th power over the square root of the determinants of the two Dirac operators, the fermionic ones and the bosonic part. But we can do something spectacular here using the notation from supersymmetry. Let's say we have a Z2 graded matrix called a supermatrix, and let's say that we call this the matrix M. Let's make this a diagonal supermatrix, a Z2 graded matrix, in terms of the Dirac operator. So let's have the fermionic part here, and then the bosonic part here and zeros elsewhere. This is a supermatrix graded between the fermionic and bosonic parts. So with this matrix M, we can now write this even more simply as pi to the 4th power over the square root of what's called the Berezinian of the supermatrix. We also call the Berezinian the superdeterminant. And so we're going to write this as S determinant, the superdeterminant of our supermatrix M. And that, my friends, is our final answer, which I think is a very, very elegant answer, if I do say so myself.
you.